what we basically did last time is we looked at the classical utility maximizing model and talked about getting from there to the Marshallian demand curves with a stop along the way at the first order conditions. So let me just put that back up on the board. So the problem we started with was maximize utility, which we said depended on many goods, x1 up to xn. And as I said before, one of the toughest parts of this theory is really that we don't have a whole lot of ex-ante information about what this utility function looks like, nor do we actually get to see it. You know, we'll contrast that with what we'll talk about later in the quarter, which is a production function. For example, you know, these might be the inputs to what you use to produce corn, but the big virtue in the corn case is you actually get to see the corn, right? You actually get to see what's being produced. As here, we just have this thing called utility that we don't see. In either case, we think they're choosing the inputs in some sense to get a lot of output, but in the case of utility theory, we don't really directly see the output, right? That's going to be one of our big handicaps. And it's going to turn out, when I talk about it later, to be one of the reasons we're in some sense going to want to minimize the role of utility in what we talk about. We're going to really actually want to maximize the role of something like production. And fortunately for us, I think production really lies at the heart of much of this analysis anyway, but we're really not there yet. So we want to maximize that subject to a budget constraint. And the most common budget constraint is the one I wrote down last time, which is a linear budget constraint that comes out of a market economy where you can buy as much or as little as you want at prices. But we could easily substitute a nonlinear budget constraint and come up with a very similar kind of analysis. In fact, we'll see later how you can use this same demand curves we came up here in the context of a nonlinear budget constraint. Okay. Anyway, so that's going to be our problem. We set up the Lagrangian for this, which is a simple technique for constrained optimization. And that was just u of x1 up to xn plus lambda m minus the sum of the xi pi. And we said the critical or first order conditions for this are partial u partial x1 equals lambda p1 down to partial u partial xn equals lambda pn, and the budget constraint itself, xi pi I equals 1 to n. And we just assumed you exhausted your budget, which is a pretty weak assumption, right? As long as you have something you value spending money on, in this problem, you'll exhaust your budget. Even if you got tired of n minus one of the goods, as long as there's one good that you want more of, you're going to exhaust your budget. You'll just spend whatever's left on that one good. So pretty weak conditions where you exhaust your budget. So you see often in textbooks people talk about the case where people are satiated or whatever. I'm not going to bother with that. I've never found an empirical use for that. It never seemed like a constraint that I wanted to loosen up. So anyway, so that's going to be our result. And so the solution, remember what this is. This is this proportionality relationship between margin utility and prices. And that was important for many things. First off, we don't directly see marginal utilities. So this theory says, while I don't see marginal utilities, I do see prices, and I can infer marginal utilities up to a factor of proportionality from prices. That's a really important result. That was the one we used last time to be able to talk about whether utilities going up or down, aggregate across different kinds of goods. There's all kinds of things we can do based solely on that proportionality. Because the idea that this person is maximizing tells us that in equilibrium, those marginal utilities of those different goods, which I can't see directly, right? I can't look at his eyes and say, this is your marginal utility. I can't measure that. But I know if he's optimizing, it's proportional to prices, and I can go in the grocery store and see the prices on the shelf. So I can see these and therefore infer something about those. That's really a key part of it. Now, these proportionality restriction, which comes down to, like we said before, some notion of marginal value equals marginal cost, right? That's what this is. Or utility per dollar being the same across all the goods, but that's really the same statement. All those things, together with the budget constraint, get us to those Marshallian demand curves I talked about last time, which express his equilibrium choices as a function of prices and income. Okay. Now, people, we don't always push this notion as hard as we can, but in a strict Marshallian view of the world, one thing you'll notice is that there are no quantities in our expression for the demand for X1. Right? So for example, when I'm thinking about the demand for toys, I don't have the number of kids in here. Right? If I'm thinking about household demand for toys, I don't have the number of kids. Or if I'm thinking about the demand for gasoline, I don't have the number of cars. Right? What does that mean I'm assuming? I'm assuming that kids don't matter, cars don't matter? Yeah?
When you're measuring the demand for gasoline or toys, holding fixed number of kids?
No, I'm not holding fixed the number of kids or cars. Yeah?
It's incorporated in prices.
Right, so what am I implicitly assuming? Like, for example, take the gasoline case. What am I assuming? Well, I don't have the quantity of cars in here. I got the price of cars in here. That you're optimizing. Therefore, the cars are responding. As I change the price of gasoline, the response that the Marshallian demand curve is going to give me in terms of the price of the quantity of gasoline. So I lower the price of gas from $3 to $2. That's going to increase the quantity of gasoline, presumably. It's going to obey what we call the law of demand, even though we haven't talked about it yet. I think we know enough to know that's where we're headed. What are we assuming about cars? Implicitly in this formulation of the problem.
Number of cars can change.
Number can change, and not just the number of cars, the kinds of cars. Our cars, what's going to happen? Our cars are going to get bigger, we're going to have more of them. We're going to do all kinds of stuff. So we're implicitly assuming that the number of cars, as well as the number of buses, as well as where I live, as all them other things are changing as I change any one of these prices. Remember, people understand that? That's the idea. The idea here is that these are mediated through the prices. Okay? Now, we'll come back later and say you can put quantities in here inconsistently with this demand system here, but we're not ready to do that yet. But as stated, we're assuming those things are adjusting. Well, you might say with cars, well, that maybe not such a great assumption, but you could do it. What about toys? Yeah, exactly. You could say, well, the number of kids are going to adjust. Right? We got that adjusting in here too. Right? We got all that stuff. So there's a lot going on here in this demand system. Just wanted to point that out. Okay? So sometimes when you're doing empirical work, you might want to think about whether, is that really what I'm looking at when I see the data? Am I really letting all those things vary? And we'll come back to say how things will change if those things all don't vary. All right. Any questions before I move forward? Yes? Well, but that wouldn't, probably what will happen if the price of toys goes down is we'll have more kids and more toys per kid, right? That's probably what we would expect. But why would we think that we wouldn't get a response in the number of kids? But empirically, we would think that's part of the story, right? You could think about a world where the number of kids is fixed. Right? You could think about that. But let's say, and in the case of toys, you might argue, when we talk a little more about magnitudes and what determines magnitudes, you might argue maybe this isn't going to be that important, that the number of kids are going to change. But let's say I did a different question. Let's say I made daycare cheaper. I lowered the cost of taking care of kids. Probably wouldn't want to hold the number of kids constant in that experiment, right? If I'm going to say I'm going to go from a world where I'm going to have a substantial subsidy to taking care of kids, holding the number of kids constant probably wouldn't be a very good assumption, right? Now you might think about why it might work okay for toys and not work okay for daycare. Okay, you want to think about why. We'll come back to that. Hopefully something we'll put on the board today will help you understand that. But nonetheless, I definitely want you to know that these demand curves are really, and we sometimes forget this, we're sort of, the story here is that when one price changes, I'm not just responding on that margin. I'm adjusting my whole bundle to adapt to that price. And one of the things that, sort of you get as you start looking at the world is that often price changes have broad effects. They affect not just that good, they affect lots of other things that people do, okay? As computers have gotten cheaper, it's not just changed the way we calculate, numbers or how we do spreadsheets or whatever. It's affected a wide range of our life and the goods that we consume and how our lives are organized. I mean, it's just had broad effects. And that's the kind of thing you want to think about happening. All right. Now, this is one approach to thinking about the consumer's problem, and it's probably the most natural approach because it seems to fit with the way we look at the world, right? That is, I got a budget, I go out in the marketplace, I got a bunch of goods I can buy, and so this maximization problem kind of looks directly at what I as a consumer might think about the problem I face. Turns out there's another way to look at this that's very helpful and actually has a lot of its own empirical applications, and that is to turn the problem around and consider what we would call the cost minimization problem. So the cost minimization problem is, in mathematics, would be the dual of the problem we just talked about, would be, let's find a bundle to minimize the sum of the xi pi subject to u of x1 up to xn equals some specific utility level u bar. All right? So we've tried to turn the problem around. Instead of saying, what's the maximum utility I can get for a given income, I've turned it around and say, how much income do I need to achieve a given level of utility? Now, people understand why those are dual problems. People understand why those solutions are going to be related, right? It's x1. Think of the two good cases, x1, x2. I got this solution. This is u of x1, x2 equals u bar. This is some m over px, p1, m over p2. And you might ask, is this guy maximizing utility subject to that budget constraint? Or is he finding the least budget he needs to get to that level of utility? And the answer is, I don't know. Looking at the picture, I can't tell you which one he started with. But that same point is going to characterize both of those, right? That is, this is just going to be a dual way, reverse way in some sense of looking at the same problem, right? You could say, I wanted to get to this indifference curve and I kept switching my budget in until I got to the minimum budget that would allow me to get to that curve. Or I started with this budget and said, what's the highest curve I can get on? Those two things are going to end me at the same point, right? People see why those two problems are so closely related. Okay. All right. So how are we going to solve this problem? Well, we can look at the Lagrangian for this problem. L is the sum of the xi pi, plus I'll call a different multiplier mu, u bar minus u of x1 up to xn. Okay, so that's my dual formulation of the problem. I'm now going to minimize cost subject to a utility constraint, reaching that level of utility. Now, there are real-world problems for which this might show up. You might say, look, I'm trying to get an employee to move to someplace else from where he lives now, and he has a certain salary and level of utility where he is. In order to make him at least as well off in the new place, and they have different prices, I'm going to have to give them a different level of income. I mean, how much income do I need to give him to allow him to be as well off living in New York as he would have been living in Chicago? That would be the kind of question. How much of a bump or decrease in income can I get away with sending him to New York instead of living in Chicago? All right. Any questions that people have? All right. Now, what are the first order conditions? Well, we take the derivative with respect to each of the x's, and those derivatives are going to be pi minus mu partial u, p1 minus mu partial u partial x1 down to p1 or pn minus mu partial u partial xn. These all got to be 0. And u of x1 up to xn, of course, has to be equal to u bar. Okay? Those are my corresponding conditions than what I had before. Now, I can rearrange these to be p1 equals mu partial u partial x1 down to pn equals mu partial u partial xn, and of course just that same constraint, u of x1 up to xn equals u bar. Now, the thing to recognize is that these n equations are exactly the same ones I had before. It's just got mu in place of 1 over lambda, right? Mu is just the same as 1 over lambda. And therefore, that same interpretation that margin utilities have to be proportional to price has to hold for the cost minimization problem, just like it did for the utility maximization problem. For the same reason, right? If I got more utility per dollar on one good than another, then I should shift my dollars to the one that gives me more utility per dollar. I mean, it's the same question. It's not even a different question. And that's why both of them are characterized by this tangency, where there's the same slope between the budget line and the indifference curve. Everybody understands that, right? It's the same equations. Same equations. Now, the only difference is I'm finding a solution of, so the way I think about it is there's a whole bunch of these solutions that look like that, right? Take the two good case. I got that solution, I got that solution, I got that solution, I got that solution, I got this one over here, right? I got a whole bunch of these solutions. There are all these tangency conditions that are representing for some value of mu that satisfies this equation, right? Those are all those solutions, they're all these ones, which are the same set of solutions I got here. And then what I'm doing differently is just how I'm labeling those equilibrium points. In the one case, I'm labeling by the utility level you're on, and in the other one, I'm labeling by the budget line you're on. People get the idea? It's the same set of points, it's just one case it's indexed by the utility level, and the other case it's indexed by the budget level. So just like we solved those earlier equations, we can solve these equations for what we'll call the Hixian demand curves. And the Hicksian demand curves are x1 equals x1h. I'll put an h for Hicks instead of Marshall. x1h of P1 up to Pn U bar. Okay? Down to xn equals xnh of P1 up to Pn. Okay. All right. So now a different set of demand equations. But critically, and this is what confused me when I was a student taking this, so maybe you're going to get confused by the same thing, which is, but they don't describe a different set of choices. They describe the same set, they just index them a different way. Right? So go back to this point. This quantity here, x1 star, that's the equilibrium choice of good 1. x1 star would be equal to what? How could you describe it in terms of the Hicksian system? It would be x1h of P1, P2, and U bar, right? Because this is the indifference curve U bar. I could also say it's also equal to x1m of P1, P2, and m, where m is the value that associated with that budget line. People see that? It's the same point described from two different points of view. Right? People see that? That's the difference between the Hicksian and Marshallian demand systems. It's not a different set of choices. It's the same set of choices described from a different perspective. In the one case, I'm indexing that choice by the utility level achieved. In the other case, I'm indexing that point by the budget amount that he's spending. That's it. That's the only difference between the two. Okay? All right? Any questions that people have? People understand that, right? So now I got two ways of thinking about the consumer problem. I can think about the consumer problem, kind of what we call the direct solution, which is think about maximizing utilities subject to a budget constraint. That yields a set of Marshallian demand curves that describe the consumer's choice as a function of prices and income. I could then rethink about that problem from the other perspective as a cost minimization problem where he's minimizing costs subject to a given level of utility, which leads me to a set of Hicksian demand curves, describes those same points, not by the income that you required, but by the level of utility achieved. That's the two systems. Question, anyone? Is it clear, right? Or not? I mean, you got to let me know, because, I mean, I'm looking out there and everybody's just looking back. Yeah, okay, everybody's good. All right. I got one thumbs up, so at least somebody knows what's going on. Anyway, all right. So what can we do with this? Well, ultimately, as economists, we want to be able to use this theory to predict stuff, right? Everybody agrees with that. Right? Otherwise, we're just having fun. I mean, it's not even that much fun. We could do a lot of other things. If we couldn't use it, we could find much more fun things to do. All right, so we want to figure out how we're going to use this. Okay. Why is the cost function concave? In fact, I'm going to prove, everybody agrees this is kind of like, that one's a pretty easy one. Everybody would agree this one's kind of pretty easy too. So the only two that are kind of tough are really these two. This one and this one. Right? Those are the two that are sort of tough. And that's what we're going to prove right now. Okay? And I'm going to prove it first in kind of a graphical way that'll show you the logic behind why it's concave. And then we can come back in a minute and prove it more broadly. So I want to think about it in a unidimensional case. And you could actually think of it as a multidimensional case. You just would have to be moving along some vector, but I'm not going to care about that. I'm going to think about here's the price of good J. And in my experiment, the only thing I'm going to be moving is the price of good J. And I'm going to start out at some PJ naught. That's the initial price. So I got PJ naught and P1 naught all the way up to PN naught, right? I got all my prices got some initial number. And I'm going to assume that I have some cost at that initial point. So this is some cost minimizing point. This is C of P1 naught up to Pn naught U bar. That's my cost. Okay. And I know that point. That's my starting point. And then I'm going to say, how does my cost vary as Pj moves? As Pj changes, how does my cost vary? Okay? And I want you to consider a kind of stupid solution. Okay? This is like the monkey solution, right? This is like I'm not thinking at all. As the price of good J changes, I'm not going to do anything. I'm not going to change my bundle at all. Now, that's not the optimal response. Everybody would agree. Could be the optimal response, typically not. Right? So as an initial starting point in my mind, I'm going to say, how would my cost vary with PJ if I didn't change my decision at all? Well, what would happen? Well, I would move straight along a line, right? I would move along a line that would be linear in P. Like say I'm consuming 10 units of good. Say at this point I'm consuming 10 units of good J. Then for every dollar I raise the price, how much is my cost going to go up? $10. I'm going 10 units, and every dollar the price goes up, I pay $10 more. And every dollar the price goes down, I'm going to save 10 bucks. But he agrees with that. So I would be moving along a line, and the slope of that line equals xjh of P1 up to Pn naught U bar. So if I didn't do anything to adjust my bundle, I would move along that line. And that line has slope equal to the Hicksian quantity. It's also equal to the Marshallian quantity, by the way. It's equal to the quantity, right? It's 10 in my example, which is both the Marshallian quantity and a Hicksian quantity. Okay? So whatever that quantity is, I would move along that line. Now, if I adjust my bundle, if I make an adjustment to my bundle, I can't do any worse than this. Right? This is the worst I could do. I mean, the optimum got to be at least this good. Because the best solution is always better than the stupid solution, right? It's got to be at least as good. Therefore, my cost function has to be below both on the left and below on the right. All right? So now you see the logic. It has to have that slope precisely because and it has to be concave because the worst case would be linear, right? If you couldn't adjust at all, it would be linear. If you can make some adjustment, it's going to only adjust to make it concave. But we also now get an idea of how concave it's going to be. If the optimal adjustment is strong, that I'm able to adjust a lot, then this thing's going to be quite concave. Because it's going to have slope 10 at the beginning, and then I go to 9, it's only going to have slope 9. Then I go to 7, and it's only going to have slope 7. Right? It's going to be getting curved. And the more curved it is, the more adjustment this guy must be making. So the idea is, I started with this function that was inherently linear. And by minimizing that function, I'm going to make it from linear to concave. Because I couldn't make it convex. That would be going in the wrong direction. I'd be like doing something stupid. As long as I do something smart, I'm going to move this in to make it concave. and the slope is going to be equal. So that's really what lies behind it, right? Now you can jazz this up because you could say, look, really let's not start with some just moving just PJ, moving some direction, then same story. Doesn't really matter. Okay? Any questions that people have about that? So we can prove, yes?
Is there a direct relationship between the curvature along one price dimension and the elasticity for that good?
Absolutely. Because think about it. Think about the slope is this. So that's so C partial Pj equals xjh of P1 up to Pn u bar. You agree with that, right? So then partial squared C partial Pj squared would be equal to, which is how curved it is partial xjh partial Pj, which is how responsive is the quantity of good J to its price. So there's not just a slightly direct relationship, there's an extremely direct relationship between those things for the reason that I said a moment ago. At this point, the slope is 10. Why? Because I'm buying 10. At this point, the slope is only 8. Why? Well, the only way that slope can now be 8 is that I'm now buying 8. And the only way that slope can get down to 6 is I'm now buying 6. So this thing can only be as concave as this quantity is responding. This is not magic, right? The idea that some people, sometimes when people first learn this, it sort of seems like magic. Wow, that just happened to turn out that way. It's not. It doesn't just happen to turn out that way. It has to be that way. The only way this slope can get lower is that the quantity gets lower. That's it. That's the only way. If the quantity ain't getting lower, the slope ain't getting lower. Right? It's not like some magic of mathematics. It's necessary by the economics. All right. Any questions that people have about that? People understand how that